Um, Think Neuro 2024 Summer Clinical Research Internship, investigating brain-computer interface-induced neuroplasticity for stroke recovery. The background. Brain-computer interfaces, also known as BCIs, or brain-machine interfaces, also known as BMIs, essentially are devices which decode neural signals and translate such into actionable outputs. There are two main types of BCIs/BCMIs. Non-invasive BCIs record data without requiring surgery. Some examples include electroencephalography, also known as an EEG, which is the most widely used and records with scalp electrodes. Magnetoencephalography, or an MEG. Functional magnetic resonance imaging, or an fMRI, and functional near-infrared spectroscopy, or an FNIRS. Invasive BCIs are directly implanted on the brain and require surgery to record neural signals. Some examples include microelectrode array, or an MEA, electrocorticography, ECOG electrodes, stereo electroencephalography, SEEG electrodes, and deep brain stimulation, DBS electrodes. The graphic shows neural recordings, which have the three listed, neural data, which then goes into a decoding algorithm, then an action or motor plan, which has an artificial system, which is like examples include computer cursor and prosthesis or orthosis. And then finally, it delivers a feedback delivery, which could be visual, auditory, or tactile, or proprioceptive. Um, Neuroplasticity. Neuroplasticity, also called neuroplasticity and brain plasticity, is the ability of the nervous system to change its activity in response to intrinsic or extrinsic stimuli by reorganizing its structure, functions, or connections, referred to in the first image. Such is a pivotal mechanism underlying motor recovery, as it allows the brain to adapt to external and internal changes. Brain-computer interfaces are a unique method of inducing neuroplasticity, as such can significantly improve outcomes for those recovering from motor injury. Stroke. There are two primary types of strokes: ischemic stroke and hemorrhagic stroke. Ischemic stroke occurs when the blood vessels within the brain are strained or blocked. Hemorrhagic stroke occurs when blood vessels within the brain rupture or leak. As strokes can cause devastating impacts to motor ability and function, BCIs which induce neuroplasticity can significantly improve outcomes for patients suffering from stroke.
Okay, so just a little bit about our research question and our objectives. So primarily, our research question is focused on research that's been conducted so far globally on the usage of BCI or brain-computer interfaces, as a reminder, induced stroke recovery, and what type of insights do they provide for future research and as potential methods for stroke recovery and their practicality. And the reason we chose to cover BCIs, especially in the application of strokes, is that stroke is one of the leading causes of death annually, as nearly 800,000 individuals suffer from strokes worldwide. And so far, there's surprisingly very little meta analysis examining current literature and current treatments for strokes. So, a few of our objectives are as follows. We wish to identify various patterns in the type of BCI technology used, and the means we'll do this through is by seeing the specific amount of methods and the reported outcomes by analyzing the top 100 most cited articles of the Web of Science. And additionally, we wish to pinpoint and assess the quality and rigor of existing studies and identifying core strengths and weaknesses in particularly underrepresented or underexplored or under-researched BCI techniques and typically neglected patient populations within our research landscape. Also, we wish to synthesize and come up with and conclude meaningful insights about the effectiveness of certain BCI techniques in order to improve rehabilitation outcomes and to boost brain neuroplasticity by removing irrelevant studies. So, by doing this overall, we'll hope to sort of trim and define the most relevant and the most practical means of using BCI technology as stroke recovery. And additionally, just one more thing are particular gaps not just within the current literature, but technological advancement globally within BCI technology for stroke recovery. And here's our methodology. So, a team consisting of several members decided to extract the top 100, once again, top 100 cited articles from the Web of Science that particularly pertained to the use of BCIs and neuroplasticity, and we used the bibliometrics package from R and Google Sheets to perform bibliometric analysis in which we investigated and identified several key trends. And these key trends had to do with publication patterns over time, most important and influential authors in BCI research contemporarily, and the institutions, so the underlying undergraduate institutions, research themes, sort of collaboration networks between authors, such as which authors cited other authors and their prominence and relevance to the field, and additional emerging topics within the field and how the field is dynamically changing. So, once again, to reiterate, some of the software we used was the Web of Science Core Collective, which is the WOSCC, RStudio, Bibliometrics, or Google Sheets, but you can optionally use Excel or any other sheet formatter. And within, you can kind of see this flow chart here within our Web of Science search. So at first, we grabbed around 219 articles. We decided to concisely trim it to around 100. And these particularly consist of 69 unique articles and 31 literature reviews.
Yeah, so figure one, you can see here, allows us to view the widespread growth of research within the field, measures abstract trigram frequency over time, and was created in BiblioShiny. As years progress, you can see that the diversity of trigrams continue to grow, but the overall dominance of brain computer interfaces over other trigrams was recurring. Other notable trigrams include chronic stroke patients, which had 9 cumulative occurrences until plateaued 2020 and onwards. Functional electrical stimulation, which had 11 cumulative occurrences until it plateaued 2020 and onwards. Transcranial magnetic stimulation, which had 7 cumulative occurrences until it plateaued 2017 and onwards. And spinal cord injury, which had 6 cumulative occurrences until it plateaued 2018 and onwards. You can see in figure 2, different trends in research as time has passed. Figure 2 measures trend topics over time across all top 100 most cited articles. You can view some trend topics which have had high frequency over multiple years, such as BCI training, electrical stimulation, motor rehab, neuroactivity. Furthermore, we can view topics which have had a great deal of frequency in most current research, such as topics of perinatal stroke and upper extremity, despite such not occurring as a trend as often in past research. For example, perinatal stroke had term frequency of 7 terms in 2021 and 2021 only, whereas other topics such as motor imagery have had research conducted over a greater period of years. See in figure 3, we can see development of abstract trigrams along with the relevance of such. Notable results include the high development and centrality of magnetic resonance imaging, the high relevance but relatively low development of functional electrical stimulation, or FES, and slow cortical potentials, and the lesser relevance yet high development of amyotrophic lateral sclerosis and activity-dependent brain plasticity. So figure 4 allows us to view the institutions of senior authors with multiple papers of the top 100 cited papers. The table adjacent to it allows us to view senior authors themselves, and with this representation of our data, we can view that senior authors Cohen and Garibaghi held the highest frequency of senior authorship within the top 100 most cited papers at the time data was collected. both in 5 papers. For Cohen's institution, it was an NIH, and Eberhard Karlsruhe University Hospital for Garibagi. The other 2 most relevant senior authors include Chenoy and Birbaumer, who were affiliated with the University of Pittsburgh and the IRCCS, Hospedale and San Camillo, respectively. See Figure 5, we can see most relevant affiliations among the top 100 cited articles, as opposed to merely the senior author institutions with multiple papers. With this in mind, we can see the University of Tübingen, University of Calgary, and the University of Wisconsin were the most relevant affiliations, with the University of Tübingen having been affiliated with 29 articles, Calgary with 21, and Wisconsin with 19, respectively, though all institutions are important here. In Figure 6, we can see the most relevant sources and the number of documents that were published through such sources. It allows us to view the overall diversity in journals producing papers on BCI-induced neuroplasticity, as demonstrated by this graph. We can see that Frontiers of Human Neuroscience and Frontiers in Neuroscience were quite dominant in producing sources. However, Frontiers Neurology and these other 5 documents lag behind, but still have a very high amount of documents in the top 100 most cited articles. And finally, in Figure 7, we can see the most globally cited articles created by BiblioShiny, in BiblioShiny. You can see that 2 overwhelmingly most cited articles were published by Dali and Ramos Murgel Dai, with 746 citations and 629 respectively.
This is a discussion and conclusion. This is the overall summary of the results. Research into the use of BCI-induced neuroplasticity for stroke recovery has diversified significantly in recent years, as indicated by the various frequency of topics over time, indicated by figures 1 and 2. While exhibiting high degrees of sensuality, functional electrical stimulation had a relatively low level of development, which may indicate a lesser amount of research conducted on such within the top 100 most cited articles, demonstrated in Figure 3. The high centrality and development of magnetic resonance imaging may attest to the great deal of research conducted on applications of such. Most cited research on BCI-induced neuroplasticity for stroke rehabilitation has had notable affiliations with institutions all over the world, shown in institutions listed in the figures 4 and 5. For example, the University of Tübingen, the University of Calgary, Shanghai University of Traditional Chinese Medicine, the NIH, and the Eberhard Karls University Hospital. This may point to the widespread interest over the world in connecting research into such applications of BCI and attest to the need for collaborating in research to advance the field. Overall placement of research is needed to ensure the best outcomes for stroke patients. Our graphs point to the areas of research which may be central to the stroke rehabilitation with BCI-induced neuroplasticity, which may assist shaping future research. Limitations of data. While this study shows that it allows us to gain a broader view of the use of brain-computer interfaces, induced neuroplasticity for stroke recovery, there are overarching limitations which must be considered. For example, the limitations of the meta-analysis. Meta-analysis is inherently limited to the articles collected. As our study only analyzes the top 100 most cited articles, any article outside the top 100 will not be taken into account. Even if such an article addresses gaps in research that appear when analyzing the top 100 most cited articles. Query used. Our data was collected by searching the 3 primary terms into a Road of Science CC advanced query. As such, any articles outside of such were not taken into consideration. Conclusion. In summary, this meta-analysis has mapped the research trends in BCI-induced neuroplasticity for stroke rehabilitation, highlighting significant growth and interest in this field. Key findings include the central role of BCIs in promoting neuroplasticity and motor recovery, while also identifying gaps in long-term success evaluations and method optimization. This study underscores the need for standardized protocols and increased investment in BCI research. Unexpectedly, it reveals emerging areas like integrating BCIs with other technologies and exploring new neural mechanisms, indicating rapid evolution in the field. Future research should focus on addressing these gaps, standardizing methodologies, and further exploring new approaches to enhance the effectiveness of stroke rehabilitation strategies. Acknowledgements and references. Thank you to Think Neuro, the University of Washington, and Clearville for making this research possible, as well as each author's respective institutions. Thank you.